Hi. In this lecture, we talk about the data types in C++. Most of this probably is going to be a review for you, but this is going to be important for us to talk about data structures, so we're going to review this together. Data types. What is data type? A data type is a set of values together with a set of allowed operations. This seems like it doesn't say much. Well, that's essentially, it tells you sort of like is a class of a data, a category of data that what are the values that you can put into this particular data type, and then what operations you can do with it. And it sounds a little bit like a class because, well, class is a data type, but there are different categories of data types in C++. There's different ways of categorizing the data types, but here's a simple way of categorizing. There's a simple data type, structured data type, and pointers. What's the special data type? Let's start with the simple data types. In simple data types, you're probably most familiar with in pretty much any programming language. You have those typical things, the integral numbers, the integers. Right? Those are, in C++ you get char. Now char is a single character, and short, integer, long, long, and a various different variations of assigned versus unsigned. Then you have floating point integers, floating point numbers. Floating point numbers are decimal numbers essentially. And then you have enumeration, enums. The enums are usually user defined with the keyword enum. So here are some examples. Integers. So this is stored with 4 bytes. And so there's a range of values that are valid for this type. If it's outside its range, then you cannot use this data type. You have booleans, which are essentially the true and false values, and then you have a char, which is a character in a single byte, and then you have a long. Well, long is 4 bytes. You have a long that's 8 bytes. So int data type. We don't have to go through this. This is a very simple Boolean type, true and false, char is a single character. Well, when it comes to characters, there are different character data sets. For example, ASCII has 128 code points, and each of them represents a different character. Some of the characters are not displayable. And then there's a thing called the collating sequence. Collating sequence is basically the ordering of the characters based on the character set code. You may have Unicode, which is another common character set that supports international languages. Okay, floating point data types. Floating point there's a scientific notation in mathematics, and then when it is represented in C++, you use this format with a E in between the fractions and also the power portion of the scientific notation. These are just some examples. There are mainly two types of floating point data types, floats and doubles. Floats are having a range of 4 bytes, and double is stored with 8 bytes, so it's much larger numbers. There's actually a type that's even bigger than double, but we don't need to introduce it here. And then the min and max values are system dependent. When we talk about floating point, we need to consider the precision of the floating points. The precision is basically about the number of significant digits or decimal places. And here it shows the maximum number of significant digits for double is 15. Maximum number of significant digits for float is 6 or 7. To declare a variable, you must specify its data type. And here's a simple declaration statement for a variable. Here's some examples. You declare a variable with an int, double, or char. Now you have assignment statement to assign a different value to a variable. And then what if the value assigned on the right-hand side of the equal, is different type from what's on the left-hand side? Let's say your expression, it's a integer, and then your variable is actually a double. And what is going to happen? So there's two. This involves type conversion. There's implicit type conversion, and then there's explicit type conversion, or type coercion, same thing. And in the new C++ version, this is also called casting. This is all talking about the same thing: converting, coercing, or casting. And the implicit type conversion is done automatically by the compiler, and which can be unsafe, leads to some unexpected results. It is probably good practice if you intend to convert, cast a type to a different one, you want to make this explicit. And there's different operators you can use. Static cast, it's one of the most common. And this is the angle bracket is the type, and this is basically a templatized way of casting some value to a different type. We'll see some examples right here. So the static cast, this is from a floating point to an integer, and this is what you get. And then you can convert from an integer to a double. And then you can convert from an expression. Here in this expression, you have a value of 15. That's an integer by default as a literal. And then you cast that to a double and use that in expression. Then this whole expression becomes a double as the result. And you're converting that to integer. And this is kind of how that comes out. The result of that is 15. Let's look at another data type, string type. Now, string type is actually a type defined in the standard library. It is not a built-in initially, but this should be treated as a built-in. Whenever you want to deal with the text, manipulation, a string type is pretty much what you want to use. A string is basically a sequence of 0 or more characters enclosed in double quotation marks. And there is a null string. A null string is basically a string with no characters. The length of a string is the number of characters in it. Well, it doesn't matter if this character is an ASCII character or a Unicode character. That's counted as one character. So to use string type, you may include this header file. And if you include an IO stream, typically if you want to deal with printing to the console, and then that string is also included, you don't need to include it again. But if you do include it, it doesn't hurt. Now, the second category of data types is called structured data types. The structured data types is a little more complex than the simple types. For example, an array is essentially a sequence of elements. Each element is a data, it's a data type, has a data type by itself. And then you may have structures, and then unions. Now structures, it's a complex type that you may have many different variables as a member of that structure, and then you can also have functions that operate on those members. And then you have a union. Union may, it's kind of an unusual data type that doesn't get used much. But basically what a union is a data type with, sort of shared, like you can have different types of members as part of the union, but in any instance of the union, at any point of time, is only referencing that one member. Essentially, they're sharing the same space, and the size of that union object is basically the longest, the biggest variable of that union. The structures and the classes are very similar. Now, structs come from C. Now, in C++, of course, the features of structures have, improved quite a bit. And so it's almost the same as the classes, except some, very small differences. For example, the default access specifier for members and the base classes, that is different. Now, it's public for structures and private for classes. And then when you use a template type parameters, you can use classes in there, but not structures. Those are just minor details. But then in general, I would say classes are preferred. And it's, not necessarily you cannot use structures, but structures is sort of a redundant in a way. Now let's look at the classes. So this is the general syntax for defining a class. You have an identifier, the name of the class, and then you have a members list, variables and functions. Now here's a simple class. Now this is using plant UML as a tool to generate a class diagram. And this is essentially a UML specification of a class. The minuses are private members, pluses are public members, and then you also have pound signs representing the protected members. And so you see there's some variables, some functions. And then once you have this specified, it can be generated into a a diagram like this. Pointer data type. Now this is the third category of data types, pointers. Pointers are a special feature of C++ and C. And in C++, the pointers are a little different. Now, a pointer variable is basically a variable whose content is a memory address. It tells you where some content is located in memory. When it comes to pointer data types, there's really not a specific name associated with the pointer data type. There's many pointer data types. Essentially, it's like a compound data types. You may have, for example, char asterisk. That's a pointer, data type. So here's a general syntax to declare a pointer variable. You have some kind of data type, and then you have asterisk, and then you have an identifier. Now this data type with asterisk, that's a pointer data type. So essentially it's like you have a plain data type with this asterisk, it becomes a pointer data type. So here are some examples of declaring pointers. You have an integer pointer, a char pointer. And in terms of spaces, this is all equivalent. The actual type, pointer data type, it's called int asterisk. But typically when you write in your code, this is sort of a more preferred way. You put that asterisk close to that variable name. However, you may declare multiple variables in a single statement. It can be a little confusing, actually. I would say, try to just declare a single variable per line, per statement. Combining them sometimes can lead to some confusion. And then there's this addressf operator, ampersand. Now, addressf operator, it's a way to dereference that pointer to figure out what is the content behind that memory address, which is the pointer. Here's an example. So you have an integer of x, and then you have declare another, integer pointer p, and then this p, you can initialize that with the address of variable x. Essentially, we're assigning the address of x to this p pointer. So the address of, in this scenario, you're essentially accessing the address of a variable. Dereferencing operator, well, that asterisk, you use this in declaration of a pointer variable, but actually you can also use this to access the content of a variable, of a pointer variable. As an example, this asterisk p, that gives you the content of the memory address, which is represented by this pointer p. Now, pointers, of course, can be declared to point to any kind of data type. For example, you may have a structure here, and then you declare a pointer that points to a structure. This is an address of a student type structure. Similarly, let's say you have a student object here, and then this pointer can point to that object by you're assigning the address of student object, that variable, to the pointer. Now, how do you change the value of a member of that structure? So here's one way of doing it. You dereference that pointer with asterisk operator. And then once you have that dereference, essentially this is equivalent to that student object that points to the content, the actual structure object. And they use the dot operator, which is the member access operator, to access the member of that structure. So this is one way of doing it. And then alternatively, you can just use a arrow operator. So essentially you can do student pointer arrow GPA equal to 3.9. That's the same thing. So in fact, this is probably a preferred way of referencing a member, which is more intuitive. Now, interesting enough, if you look at this, this is almost like if you're inside a, let's say in a member function of class, you have sort of this pointer, right? This pointer, you can access the members, member variables this way too, so that you probably have seen that a lot. Now, pointer variables, they have to be initialized. So typically, C++ does not automatically initialize variables. You declare a variable that stays uninitialized until you initialize them. And the pointer variables must be initialized because you cannot access a pointer that points to nothing. And well, actually points to anything. If you just declare a pointer, that could be just in a random memory location. It is a good idea if you are not really assigning a address of something immediately to a new pointer variable. You want to initialize it to a null pointer that points to nothing. Dynamic variables. Dynamic variables are those that are created during runtime. And these variables you create using using the new operator. That's kind of how you have a dynamic variable. And so the one thing to notice here, when you use new operator to create a dynamic variable, you need to be careful about that variable. So once you declare with a new, the content of that variable is allocated on a heap, the memory location, well, memory space called the heap. And you need to make sure that memory is released sometime later when you no longer need it to avoid memory leak. And to deallocate a dynamic variable, you use the delete operator. So here's different forms of new operator. You can allocate a single variable or an array of variables. And this new operator allocates memory of the designated type. And then what it returns is actually a pointer, the location of the data that you can assign. Basically right now, if you just declare it, there's actually, it's kind of a random memory location. It's not initialized yet. You could use new operator to initialize, well, to create a int variable. Now compare this with the alternative of declaring an integer variable without using new operator. is that without using the new operator, the variable will be allocated on the stack versus on the heap. In the stack, it's a much smaller memory space that is used during function calls. When you get into a function call, it saves the state of the function call with all the variables associated with the function name, and where that function is onto the stack. And then when you exit from that function call, and that function, that basically that's called a frame of the stack, will be removed from the stack. And the size of that frame, usually you can go over more than a couple of megabytes. If you allocate a lot of data on the stack, you could get into a stack overflow error. So if you actually need a lot of memory space, you need to allocate the variable on the heap with a new operator. And variables allocated on the stack, they will be deallocated automatically, versus on the heap, you're managing it. You got to make sure they are deallocated properly. Otherwise, you have memory that's used but never released. And over time, you run out of memory. So memory leak. What we just talked about, to avoid a memory leak, a dynamic variable, if it's no longer needed, you have to destroy it with a delete operator. There's two forms here. So you can, just like with a new, you create a single dynamic variable, then you can deallocate that single dynamic variable. And then if it was an array dynamic variable, and then you use this form to deallocate that array. So with the pointer variables, the operations you can do on them are quite limited. That's sort of intentional. So one thing you can do, obviously, you can assign values to a pointer variable. And the relational operation, the only thing you can do basically is equality. You're comparing to memory location. Really the only thing that makes sense is basically whether they're equal or not. You could potentially do some simple arithmetic, like you are advancing from a array, a continuous memory block. But you have to be careful over there. Do not go over the bound that you may access some random memory location. So that it's considered a dangerous operation. So here's an example. You have a dynamic array. By doing this, so first of all, P is an integer pointer. And then you initialize with a integer array that's allocated on the heap. And this is basically 10 elements. They're initialized with the zeros. And then you're going to assign a value to this dereferenced P, which is pointing to only the first element of that array. You may advance that pointer. Now, this kind of operation typically is dangerous, but unless you're operating with an array, that is okay, but you have to know when to stop. So when you advance this, like go to the next memory location, basically that's the second element of the array, and then you can change that value as well. Now, this dereferencing operator format, you can also use this array, a square bracket element format p squared 0, p squared bracket 1, just like an array. And in fact, the name of the array is just a constant pointer, meaning once it's declared, you cannot change the value of that pointer. That's kind of how arrays work. So functions, when you are using pointers in a function, there are two things you have to consider. Are you passing the value, the parameters by value or reference? So, so if you look at this, ampersand p here, that is saying we're passing the address of some verb, some variable. If it's this is essentially saying that p is supposed to take a pointer, it's an integer pointer. But then when you invoke this pointer parameters function, and that variable you are invoking the function with, here I'm taking a reference to it. So it's basically the same pointer. It goes by, we're passing this a reference. We're not doing a copy of it. And here, you're passing a second parameter q. And this is not declared as a reference parameter without the ampersand. That means you are passing, if I invoke this parameter, this function with another variable in the second position, I'm making a copy of that pointer variable. Well, which still points to the same memory location, but it's a copy of that pointer. And versus here, it's pointing to that same location of that pointer. Now, the return value of a function may be a pointer as well. You can also use pointers to create multi-dimensional arrays. So, for example, you're declaring the board to be an array of 4 pointers. Each of the pointer points to another array. You're initializing each element of that board with another array, which you can think of as the rows of a board. So the alternative way of declaring, so this is essentially a fixed, you have basically 4 rows of the board that you're declaring here, a fixed array, or you can declare it to be a dynamic, is not fixed with a certain size, with a double asterisk here. Now, with the pointers, one of the caveat is about copying. And when it comes to copy, there's a shallow versus deep copy, because pointers point to some memory location where the actual content is stored. So when you do a shallow copy, it means if you copy a pointer variable, and then you have a new pointer variable, but that both are pointing to the same memory location. So if you delete one of the pointer variable, when you deallocate that, and the backing data is also deleted, now you have another pointer that points to, right now, some random, it's no longer a valid memory location, because that's essentially that content is no longer valid. Well, shouldn't say that it's no longer valid. It's dangerous in the sense that the operating system may allocate that same memory location that was just freed by deallocating one of the pointers and use it for something else. The data in that memory's location can be anything. So it can be dangerous if you're assuming the other point is pointing to the same data while the other thing is deleted. So that is the danger of a shallow copying. A deep copy means that you're going to also copy the content as well, not only just the location, the pointers. So now you have another copy. If you deallocate one of the pointers, then the other pointer still pointing to valid data because that content is copied as well. So here's some example. Let's say I have a class declared here called pointer member var type. And then I declare two objects here. Object 1 and 2. So in memory, they may look like this. They get it, each object has its own copy of the member variables, x, the length p, and the pointer p. Now remember, p here is the integer pointer. Now, if the object 1 goes out of scope, then its member variables are destroyed. That means that p will be destroyed as well. So that's just the default behavior. Let's say you have not done anything, and the memory space will be deallocated. So you can no longer access that memory space. That actually P is not deallocated, sorry. So take it back, because the default behavior is that the object 1 will be destroyed, but it's not gonna deallocate P automatically unless you implement a destructor. A destructor is like this. You use a tilde and then the name of the class and without the parameters. And a single class can only have a class can only have a one destructor. And this is going to be invoked automatically when the object goes out of scope. Instead of the default behavior, now you are customizing that destruction behavior with saying, okay, I have a pointer here I need to take care of. And so I'm going to delete that. Well, you may wonder, why doesn't C++ take care of this automatically? Well, a pointer like this, if you declare it with this integer asterisk, this is considered a raw pointer. When you have a raw pointer, the language gives you the maximum flexibility. They basically recognize, oh, what you want here is you want to manage that memory location by yourself. And so it's expecting you to manage that. Now, there's different flavors of pointers where the memory deallocation will be taken care of automatically. That is the topic of a different lecture if we get to that, but it's some advanced features. So essentially we can have pointers that will be taken care of a deallocation automatically. The behavior we're talking about here will be taken care of that way. But with this raw pointer, what we see here, you still have to, do this explicitly. You may have noticed here also again, this, we use this square bracket here because we're deleting an array. This is assuming, even though you see this is actually just a single pointer variable, but then it depends on what the intention here obviously is this, you're gonna assign an array to it with a new of some kind of size. So when you use a new operator, array, if that's the intention here, and then you need to deallocate with the array deallocator, with the delete array. And then the other thing we need to talk about is the assignment operator. The assignment operator means if you assign a pointer to another, well, essentially, let's say, because this is the same example, we have object at 1, object at 2. If you just assign, let's say object 1 to object 2 to make another object, do that assignment, it's going to actually, by default, do a shallow copy. And that's kind of default behavior. It will copy your pointer in a shallow way. As we explained previously, you have another, this is object 2 with another pointer here, but it points to the same content that the P variable in object 1 points to. So if you don't want that behavior, typically that's not what we want. And then we need to customize that assignment behavior by, customizing the assignment operator to avoid that shallow copying. And now there's another thing called copy constructor. And why that matters? So first of all, the default initialization is that, when you provide an object of a class, you can initialize another object with a different object. So let's say this, object, well, actually the example is right here. So you want to create a new object of a class pointer member var type called object 3. Here you're initializing it with object 1. When you do it this way, by default, it's going to be a shallow copy unless you customize that behavior. So you customize it by creating your own copy constructor where you can do the deep copy of the content of the pointer. And when you pass objects by value to a function call, it's the same thing. So by default, it's going to use a copy constructor. If you did not customize it, it's going to use the implicit one provided by the compiler, which is a shallow copy. Unless you have customized it with your own copy constructor, then it's going to use yours. And so here's an example. The way you customize that copy constructor, essentially, this is what the function signature looks like. Class name with a single parameter. This parameter is a constant pointer. Constant pointer meaning you're not modifying the content of that pointer. So we see some caveats when you use pointers in a class, which is, pretty common. So when you do have pointer variables in a class, you want to do a couple of things. You want to manage the memory. You want to manage the memory of the dynamic, the pointer as part of the class. So the things that you need to do, first, you should have a destructor. The default one is only doing a shallow destruction, is not going to deallocate your pointers, your raw pointers. And then you want to also overload the assignment operator so that you provide a deep copy when you assign an object to a different object of the class. Also, you want to customize the copy constructor so that your the copy behavior is not shallow. Well, unless that's intended, but in a lot of cases it may not be. So you kind of have to consider those things. So that's pretty much it for this lecture about data types. Thank you.